A research team from the US probably observed one of the rarest events in the universe ever. It specifically deals with the radioactive decay of the isotope xenon-124, which has so far only been predicted theoretically. And so this discovery could help us to track down the mysterious dark matter. Click some science and fiction. Here you can watch fascinating science videos thrice a week. Subscribe to the channel. Only then will you not miss out on anything. A warm welcome.
1, 2, 3.
The underground Xenon 1T detector in Italy made this record-breaking discovery possible. In fact, research teams here are looking for possible particles of dark matter, for example, the so-called weakly interacting massive particles, WIMP. They're an assumption for the composition of dark matter. 1.4 tons of high-purity liquid xenon are filled in the gigantic shielded tanks. It is rare, however, that this xenon can make the dark matter glow. Extremely rare, unlike halogen lamps or headlights, which you have at home and where it is nothing special in getting these lights to shine. But back to the experiment. A radioactive decay of the xenon-124 isotope was actually observed here, and this is a real premiere, because this decay has been predicted theoretically but has never been registered before. And this is a real first, because this decay has been predicted theoretically but has never been registered before. And that's no surprise, because the so-called half-life of xenon-124 is, attention, 18 sextillion years. Remember, 1 sextillion means a 1 with no less than 21 zeros. This is really an unbelievable amount. For comparison, our universe, on the other hand, is only 14 billion years old. The reason why the decay of xenon-124 is so rare is due to a situation that almost never occurs. In technical jargon, there is a talk of a so-called double electron capture. This could be observed only with 3 elements. To be more precise, 2 protons in the nucleus of the atom simultaneously take up 2 electrons. But not only that, this double capture of electrons is only successful if they are extremely close to the atomic nucleus at the right time. New York scientist Ethan Brown comments, "We have thus multiplied a rare event with a second rare event, which makes the whole thing ultra rare." Originally, the research team was not interested in provoking this very rare single event. Rather, the experts were searching intensively for dark matter and rare collisions. But even for this purpose, they had brought together a large amount of xenon, which, by the way, only consists of about 0.1% of the isotope. Similar to the lottery, where you increase your chances of winning if you fill out a lot of lotto tickets. In order for a single particle to decompose, the material must also be stored in a very clean and disturbance-free manner, just like a depth of 1.5 kilometers, where the very sensitive Xenon 1T detector works. And then it suddenly happened. During the analysis of the data from February 2017 to February 2018, the experts encountered flashes of light that could not originate from a particle passage. The energy content of this radiation did not match any known background source, but had to come from the shell of the xenon atoms. Detailed investigations confirmed this assumption. During the collapse in the atomic shell, electrons from the innermost shell of the atomic shell are removed, and the resulting gaps are filled with electrons that circled further out. Through this process, the electrons release energy in the form of X-rays. This could be captured by the detector. A great stroke of luck and success for the team involved, Ethan Brown. This is the first time we have witnessed this decay. This is the slowest, longest process ever directly observed. Not only that, but also the success illustrates how sensitive the detector already is and how much potential there is in this measuring method. This also applies to signals that have nothing to do with dark matter. The scientists now hope that this new finding will enable them to test the structural models for heavy atomic nuclei. In addition, the experiment is currently being modified, and the new phase, called Xenon NT is being launched. Interference signals are increasingly suppressed and the active detector mass is tripled. Ultimately, this modification will make the detector one order of magnitude more sensitive. A good step in the right direction, perhaps to solve the mysteries of dark matter soon. The chances are not slim because liquid xenon has a high density and each individual atom has many individual elementary particles with which a piece of dark matter might collide at some point. If you want to find out how close we actually are to find dark matter, click here. We would be happy if you recommend us to other science fans. Until then, stay tuned and see you soon.